I am back at the curve tracer for the analog, using the Analog Discovery for what I hope it will be the final design. On the right, you see the trace, that is the curve trace of, in this case, a 3904 transistor. On the left, you see the channel 1 and channel 2 of the Analog Discovery, and I will show you the schematic in a minute so that this will all make sense. Notice that channel 2, the blue trace, is a series of increasing values. The yellow trace, which is channel 1, is a triangle wave that repeats. Now, below, here you see a step function that is being generated by the waveform generator. In this case, this is waveform 1, and this is waveform 2, or channel 2. Notice that this is running a triangle wave with an amplitude of 2 volts and a frequency of 50 hertz, whereas this, that is the step, is running at 5 hertz with an amplitude of 2 volts and an offset of 2 volts. And we'll explain all of that a little later when we get to the schematic and so on. But what I've been trying to do is to adjust or refine the design of the Analog Discovery 2 curve tracer that I've been working on off and on for a year or two. And what I wanted to do was to get a display on which you could measure a transistor like the 3904. To do that, you need a voltage on the collector that goes to, let's say, 15 volts. In this case, it's 14.5 volts over here. And a source of stepped base currents that you can apply to the transistor to generate this family of curves. And then finally, you need to sweep the collector voltage from 0 to its final value, and using a triangle wave, we then also sweep it back to 0. So basically what is happening here is the collector voltage starts out here, moves out this way. As it does so, the collector current increases, and the collector current is being displayed on this axis, the y-axis. Then the base is stepped to a higher base current, and the sweep occurs again, sweeping out this trace, and so on all the way up. Now, if you've watched some of my earlier videos on this same thing, you will notice a few things. For one, we now have 10 total steps, and we now have voltages that exceed the 5 volts that the Analog Discovery can put out. And if you watched my immediately preceding video, you know that the way we were able to achieve that was by using a filament transformer turned backwards. Once again, I'll show you that when we look at the schematic. So first, in the interest of a little completeness, what I'm going to do is show you what I originally set out to do, and then what the final design looks like. So this is a VCE IC curve that I got off the internet. It's a characteristic curve for NPN. This is fairly typical for an NPN transistor, which is what the 3904 is. Now, this particular curve tracer will work with a variety of transistors, especially the smaller signal transistors up to low to medium power transistors. It's probably not satisfactory for high-power transistors, partly because the analog discovery can't supply the kinds of current. But nonetheless, this is the collector current, and in this case, the collector current is shown in amperes. So this would be 5 milliamperes, 10 milliamperes, 15 milliamperes. I have chosen to restrict the range to a bit less than that, once again, because of the analog discovery's current sinking capability. The voltage, as you see, goes from 0 to 15 volts. So what I've been trying to do is to create some way to amplify the 5-volt signal that you can get out of the analog discovery up to about 15 or 20 volts, which is more appropriate for a 3904 or other transistor. Now, here are some of the characteristics, the maximum characteristics of the 3904. And you notice that the maximum collector to emitter voltage is 40 volts. The setup I'm about to show you will allow you to exceed that if you wish to. The collector to base voltage can go up to 60 volts, and then the emitter to base voltage has to be below 6 volts. The maximum collector current continuous is 200 milliamps. So you can draw a fair amount of current through a 3904, but what I'm trying to do is to demonstrate a proof of concept here. And so here is the final circuit. And the way that I have operated it, or the way that I have designed it, I use a triangle wave out of waveform 2 of the, or channel 2 of the waveform generator. I then take a 12-volt filament transformer and turn it backwards. In other words, I use the 12-volt winding to drive from the waveform generator, and the 120-volt winding on the other side to produce the collector voltage. By turning it backwards, I get a 1 to 10 step up in voltage. So for every volt we apply here, we get 10 volts over here. I then put a diode in series, mainly so that we would not stress the 3904 with high reverse voltage. You don't need this, but it's a good safety feature just to make sure, particularly as you start raising the voltage, that you don't get reverse breakdown in the transistor. So what that does is turns what is in essence an AC signal into a pulsing DC signal. Then I connect waveform 1 using a step generator, which I'll show you again in a minute, through a 220K to the base to emitter junction of the 3904. This provides that stepped up base current that starts at 0 and steps up to whatever the maximum is. I've changed the collector resistor to 100 ohms. It's a good idea to have a resistor here that is as big as you can use because it helps to protect the transistor, but for measurement purposes you want this to be as small as you can get it. 100 ohms seems a reasonable compromise, though you could go lower than that if you're careful to protect the transistor by limiting the base current. Then, because this voltage now can exceed the capabilities of the Analog Discovery's oscilloscopes, which is 25 volts, I have placed a 100 or a 10K to 1K or a 10 to 1 divider on the collector. So instead of measuring the collector to emitter voltage directly, we're measuring 1/10 of it. We're applying that to channel 1. Channel 2 is sampling, and I just realized that I Yeah, I've shown this wrong. Channel 2 is actually connected over here. The other end of this is not connected to the divider. It's actually connected to the emitter, or I'm sorry, the collector of the 3904. I'll redraw that in a minute. Channel 2 measures the voltage across this 100 ohm resistor. So the result is what you see down here. We use an XY display on the analog discovery. We display the collector current on the Y-axis, which is channel 2, and we put channel 1 on the X-axis, which is the collector to emitter voltage. Then we apply 10 base steps while we sweep this collector voltage, and that produces the curves that you've seen. Now, right now I'm using a 2 volt maximum signal here on the base. If you subtract the base to emitter voltage, that means that the actual voltage across the 220K is about 6 microamperes. I'm sorry, voltage. The current through the 220K is about 6 microamperes. If you then multiply that by the gain of the transistor, which is roughly 100 in this configuration, you get a collector current of about 6 milliamperes. So, or 0.6 milliamperes, I'm sorry. So just under a milliamp. Okay, now let's go back and look at the waveform software again, and we'll talk a little about how we generated some of these signals. I'm going to move the waveform generator window up here so that you can see what I'm doing a little better, and I'm going to zoom in a little more. The top is waveform 1 and the bottom is waveform 2. Let me move this out of the way. Now, you notice that we are using a 2 volt amplitude, 2 volt offset signal, which is this stair step. The way you get the stair step is you use the custom setting, and then within custom, you choose values. Then you can enter values in this table. And you'll notice that I start with a half a volt, then a volt. Well, I should say I start with 0.5 because we convert it to voltage when we apply it to the generator. And you notice that it goes all the way up to 5. So when we do a generate, it generates this as a control signal for the wavegen. That then gets converted to a voltage. In this case, we're starting with at 0 milliseconds with 0 volts. You can see over here to the right. And then it goes up to roughly 4.5 volts. Actually, it goes up to about 5 volts total. But because we're only using 2 volt amplitude and 2 volt offset. Now, 2 volt amplitude, that means 2 volts plus and minus. So with a 2 volt offset, that means that this actually starts at 0 volts and goes up to about 4 volts. So that's the base voltage that is applied to the 220K resistor. Now, let's look at what we're applying to the collector. That is down here on channel 2. Notice that it's a 2 volt signal, and it's a, in this case, it's just one of the simple waveforms. It's called a triangle, and I have it set to 2 volts with no offset. So and one reason you don't need any offset is we're applying it to a transformer. And the transformer removes the DC component. So basically we are using this only as an AC signal. Now, one thing that some people that have tried to do this have run into trouble with is you need the triangle to run at a multiple of the step signal. In other words, you want a triangle to occur during this time, then a step, and so on. But in the waveform generator, one cycle is from here to here. So that means that you need 10 cycles of this triangle wave in one cycle of this. Or another way to put it is you need the triangle wave to run at 10 times the speed or 10 times the frequency of the step signal. So the step signal, it goes from 0 to 4 volts along this step pattern 5 times a second, or 5 hertz. And then the triangle wave that sweeps the collector is running at 50 times per second, or 50 hertz. Finally, it is important that you synchronize the two so that this triangle starts at the beginning of this base voltage and ends at the end of this base voltage, so that the next triangle starts at the next base voltage, and so on. So now let's go back and look at the scope, and you'll see what that does. The yellow trace is channel 1 and the blue trace is channel 2. So the blue trace is the collector current and the yellow trace is the collector voltage, and I'll explain this fall off in a second. Because in a real curve tracer, a professional curve tracer, you want this collector voltage to remain, the peak to remain constant. And then you step the base current, which of course steps the collector current as well. So that's what this rising blue trace is the steps of collector current that start at near 0 and then go up to the maximum value. So over here on the right, we are displaying an XY trace. And you do that, as I've shown in previous videos, by clicking on the view right here and do an add XY. That adds this window over here to the right. And right now I have channel 1 set to an offset of minus 200 millivolts and a range of 150 millivolts per division. Channel 2 is set to an offset of minus 240 millivolts and a range of 50 millivolts per division. And that gives me this family of curves. So the collector voltage starts out very near 0 and goes up to about 15 volts. Now let me show you, move the waveform generator back down here. And what we're going to do is raise, well, I didn't mean to do that. Is raise the collector voltage by changing the amplitude of the triangle. I'm going to go to 3 volts. And we're going to change this to 200 millivolts, you notice that what is happening is the curves are starting to sweep up here at the right. That is reverse breakdown. And so we are exceeding the capabilities of this particular transistor. I'll go back to 2 volts. And you see we get the family, a good family of curves again. That curve up at the end, when we began to exceed about 14 or 15 volts, actually that's 17 volts, is the breakdown of the transistor. You might wonder, well, it said 40 volts, why are we getting breakdown at 17? And the reason is that these measurements are not the peak measurements, and the voltages are RMS. Let me readjust this to get it synchronized again. So at 17 volts, we're actually, or 17 or 18 volts, we're actually applying a little over 40 volts total to the transistor, the peak voltage collector to emitter. I won't get into why that's true, but I will give you a clue. It has something to do with the fact that we're using a transformer. So when you're doing this, you do want to make sure that you keep your collector to emitter voltage within range, and you don't try to overdrive the transistor, because you can punch through the collector to base junction and ruin the transistor. So I hope that this gives you some idea of what you can do with an instrument like the Analog Discovery 2. Now, I mentioned earlier that I would tell you about this, why this voltage falls off. And you can see it over here as well. It's this would, in a professional curve tracer, this voltage would continue straight up here. In other words, this would continue on out to this voltage. So why is it only going to there? Well, it's because of the circuit we're using. So let's take one more look at that, and I'll explain it, and then we'll hopefully close this video. The reason that the collector to emitter voltage does not go to the full value of what the transformer is putting out is because of this 100 ohm resistor we're using. We call this the sense resistor. Now, if you remember earlier, I said you want as low a value here as you can get. But if you go too low on this resistor, then you'll draw too much current through the 3904. So I used 100 ohms as a compromise. It does limit the collector to emitter voltage, particularly at the higher base currents. But it also protects the 3904. And frankly, if we had been applying that 40 volt or 45 volt signal that we had earlier without this resistor, with say a 1 ohm or a 10 ohm resistor in here, we very well might have exceeded the capabilities of the 3904. Not that that would be a big loss, but then we'd have to go find another one. So this helps you avoid some mistakes by keeping this value as high as you can while still giving you a reasonable collector to emitter voltage remaining. Because remember, whatever voltage is up here drops through this resistor to the collector. So I hope that this has given you some ideas about how you can design and then iteratively improve a design to accomplish what you're trying to accomplish. When we first started out on this project a year or so or more ago, we were just using the Analog Discovery waveform generator to generate this voltage. One of the improvements was to use a transformer to step up the output of the waveform generator Another improvement was to use more steps on the waveform generator. Now we're using 10 steps. A third improvement was to lower that resistor value so that we got a higher collector to emitter voltage. And finally, to protect the inputs of the analog discovery using the 10-to-1 attenuator on the channel 1's display of the collector to emitter voltage allows us to go to voltages higher than 25 volts here while not exceeding the input capability of the analog discovery. So I hope this has been at least entertaining, if not informative, and that you'll stay tuned for some future videos. I probably will not do any more on this, but then I've said that so many times that maybe I should just say it's not my present intention to pursue this any further. I feel like that this is now at a state where you can do at least reasonable transistor curve tracing, which allows you to match transistors, to measure the characteristics of particular transistors. And by the way, you could do this, you could put a field effect transistor in here instead. Of course, what you would want to do then is you might want to remove this resistor and just control the voltage from the waveform generator, because remember, an FET is controlled by voltage, not current. But you actually could probably leave this resistor in, since most field effects draw very little base current, or gate current actually. So this curve tracer has been a bit of a project. I hope we have evolved it to the point where it's useful and it's not a professional instrument, but at least it will work over the ranges of the kinds of transistors that the average hobbyist, experimenter, ham radio operator might want to use. So if you've enjoyed this, let me know. I try to read all comments. I don't respond to all comments because a lot of times people simply want to express their opinion or make a suggestion and so on. If I see a particular question that would be generally applicable and is not explained in the video, then I will answer it. I tend not to answer questions that a person could get the answer to by simply watching the whole video. So I hope that if you have a question, the first thing you'll do is actually play the video all the way through from start to finish, paying attention to the question you were going to ask. And then if it's still not answered, then go ahead and put it in a comment. So I'm going to be moving on to some other things, but I hope you will stay tuned. And in the meantime, have a nice day.